All right, so this is an honors physics tension problem. We have a mass that is suspended by two ropes. We've got it meeting here. We have T1, we have T2. We know the mass is 5 kilograms, and we're going to use 10 meters per second squared as the acceleration due to G on Earth instead of 9.81. This is technically negative because we're going to put our forces in and they're going to show the direction. I'm just showing it as positive, but that's technically a negative. We are going to say we want to know what T is and we want to know what T2 is. And we're going to have to break this into components. So the first thing that we want to do is define our axes. So I am going to do that with yellow all the way through. So now I have my X right here and I have my Y. And then I'm going to create my little box. And I'm just going to go ahead and do it on the top. Okay, like that. Okay. And I know that this is the angle here, that this is the angle there because of the fact that these are two parallel lines. These are interior angles that are alternate to each other. So that's the alternate interior angle theorem. So this is a 30 degree. So I'm going to go ahead and put that here. And this is a 42 degree. And I'm going to label all of my forces. So I'm going to label this one as T1X. I'm going to label this one as T1Y. This must be T2X, and this is T2Y. Okay, so I have everything that I need to figure all of this out. I'm going to go ahead and put in, though, my weight force, which is acting down, and I'm going to say that's equal to mg. So really, Fg then, if I take my 5 times 10, again, the down direction indicates that it's a negative value, so I'm not putting the negative in there, is 50 newtons. Okay? So we've already broken it into components, we've labeled everything. That's half the battle, really. And we still need to keep in mind that we're really looking for T1 and T2. So these are the guys that are the ultimate challenge for us. So we know, because it's a static equilibrium problem, that we can say that the vector sum of the forces in the x direction and the vector sum of the forces in the y direction are 0. Okay, so we're going to say, make sure that this is on camera, let me go over a little bit. We're going to say the vector sum of the forces acting in the x direction is 0. And I'm going to look at my x direction. So this is my x-axis. And I'm going to use the coordinate system. This is positive, positive, negative, negative. And so I'm going to say this is really a positive T2x. So I'm going to say this is equal to T2x minus, because T1x is in the negative direction. So that's why I minus that. And I need to figure out what each one is. So this doesn't help me because I really need T2 and T1 in this equation somehow. So I'm going to use SOHCAHTOA to do that because I know the angles. Okay, I can take this value and that value and make it work. So when I'm looking at T1x, this is closest cos. So I can say this is really equal to the hypotenuse, T1 cosine 30 degrees. That's really what that's equal to. And this is really equal to T2 cosine 42 degrees. So I'm going to put that in there. So I have 0 equals my T2x, which is really T2 cosine 42 minus T1 cosine 30 degrees. I can move 1 to the other side, so because this is a negative, I'm going to move that over and make it positive. So I'm adding the value to both sides. Cancels that out, so I have T1 cosine 30 degrees equals T2 cosine 42 degrees. So it doesn't really matter which one I solve for. You can solve for T2, which means you're dividing cosine 42 by both sides, or you can solve for T1. It does not matter. So I'm going to do it like we've done in class, but again, you could solve for T2. It doesn't matter. Cosine 30 degrees. I'm doing that to get T1 by itself, because our ultimate goal is to find out what it is. So to find out what it is, I need it by itself. So then I'm going to divide out cosine 30 degrees. So really what this is saying is T1 equals T2 times cosine 42 degrees divided by cosine 30 degrees. And I can leave that like that, or I can quickly calculate what that is. I have that as my calculator says. That is what the value is. So we're going to say T1 equals T2 times 0.85810973. And this, again, has only gotten us so far. It still hasn't allowed us to solve anything. So that's just the x direction, though, of our static problem. We have two directions that we're working with, x and we have y. So now I need to look at all the components in the y direction. And I know that all the components in the y direction are 0. So I'm going to try to do this maybe in a different color to keep them separated so as not to make it too confusing. So we have some of the forces in the y direction should be equivalent to 0. And I'm going to look again at my problem. I know this is a y direction, this is a y direction, and this is a y direction. So I know that these are going up, and I've already said that up is positive, right? So these are both positives, and this is down, so that's negative. So that's why I'm assigning those values that way. So I'm going to say, it doesn't matter if I put T2y first or T1y first, right? It does not matter because they're being added. And technically, you're adding a negative, so it doesn't matter if you put weight first. It really doesn't matter the order. So if you'd said negative FG plus T2y plus T1y is the same as saying T1y plus T2y minus FG. So the order really doesn't matter as long as you make sure that you show the negative and positive math. So I'm just going to start over here. I'm going to say T2y plus T1y minus FG, or minus MG, if you want to write it that way. It doesn't really matter. I'm going to move FG over to this side. So I'm going to say plus FG plus FG. So really now I've got FG equals T2y plus T1y. But again, I'm not looking for T2y. I know that T2y, by the way, the sum of T2y and the sum of T1y should add up to this number. Why do I know that? Because it's not going up and it's not going down. Now, are they equal? No, I should expect this to bear more of the weight because it's a tougher angle, right? It's a higher angle, which means that this side should bear more of that total weight. But I know that they add up to equal the weight. If the angles were equal, these would be equal, okay? So I need to figure out what T2y really is. So T2y, when you look at it, is opposite of the angle, and this is the hypotenuse, so opposite hypotenuse. So I'm using so of SOHCAHTOA. So I can say really that this is equal to T2 sine 42 degrees. And over here, I can say, well, really, this is equal to T1 sine of 30 degrees. And I'm going to then plug in those values. And I already know what FG is. I'll just leave it as FG for now instead of plugging in 50. So I'm going to say FG is equal to, so my T2y is really T2 sine 42 degrees plus my T1 sine 30 degrees. But T2 and T1 are not able to be added because they're not the same T. It's like X and Y can't be added. So that's why this, solving in conjunction with the other variable or other component that we're looking for, is important. You're basically solving it using this plugin. So we're going to say wherever we see T1, then we can show it as T2 times that value. That will give us T1. So I'm going to sub out. So I'm going to take, what color do I want to use? Too many choices. So I'm going to take this, and basically I'm subbing it in for that value. And now I'm going to have a T2 and a T2, and that's like having an X and an X, and then I can add their coefficients. So I'm going to say, under here, I'm just going to move this over a little bit. So we can say FG is really equal to T2 sine 42 degrees plus, now I'm going to plug in this, T2 0.85. I'm running out of room, so I'm not going to write all these numbers, but I'm going to carry them. Okay, sine 30 degrees. I know what my FG is. It's 50 is equal to, I'm going to do some quick math. So I have 0.85. Sine of 30. So this is really, I haven't done this number yet, but this is really T2 times 0.429054, and around that to 9. That's a 9. You see that? And then let's do the sine of 42. So that is T2 0.66911306 is equal to 50 newtons. So let's add these two together. So alright, so I have T2 times 1.098185506, carrying as many numbers as I can. I still want T2, so I'm going to divide both sides by this number. So that gets rid of that. So I have T2 equals 52 divided by my answer. Got that as 45.529648 newtons. If we were going to sig fig this, we need to go back to the original problem and try to figure that out. So because we're using the mass, and the mass is based on 1 sig fig, this is really 1 sig fig. So 45 would round up to 50. So if you're looking at sig figs, this is really 50 newtons is T2. So that has solved only T2, but it gets easier because we can take this value and go back to our original equation. So now we can say, all right, so I'm going to use this as red to finish it off. So we say T1 is really T2, which I'm going to carry these numbers, right? Because this is a sig fig answer, I can't carry that on. So I'm going to say 45.52968. That's newtons. That's an 8. Times 0.85810973 will be my T2 value. So let me do that really quickly. 9. Oops. 429. So this says it is 39.069433395. That's newtons. So my sig fig answer is 40. So the question to consider is why this is the sum of these two is actually greater than our weight. Because it's not just carrying and pulling the weight up, it's pulling the weight up and over, which takes more force to do that. So that's why in this case, the T2 and the T1, because of the way that it is, or in any case really, even if these angles were the same, they're not bearing just the weight. They're bearing the weight plus pulling it out. And that makes the numbers higher total, right? 40 and 50, 90, as opposed to the weight, which is only 50, because it's also pulling it out, not just pulling it up. Okay, and that is probably the more complicated question that we'll have regarding tension force of a hanging object.